So what happens is the glove emulates a keyboard, and I've mapped that this touching the top of your finger is move up, touching the bottom of this finger is move down, this is move forward, and that is move back. Those map as keys, and then that's wired into the Python in the same way you did keyboard interaction, except when you touch the glove you can then move around. The glasses have the head tracking units in them, and I just wear the glasses, and when the driver publishes the orientation of my head, it's pushed into LCM, and LCM is then picked up by the Python, and it's then wired to the camera. So with the glove and the headset, I can fly around. It's a pretty simple demo. It's not great, and an Oculus Rift probably would give you a lot better behavior. You plug a Kinect into that, and then you can actually do full torso pickups. If you have perception neuron, you get even cooler than that. But, well, I don't have an Oculus Rift, and I haven't got perception neuron yet. So until we really get those pieces of equipment, this at least just demos the principles. To show that, you know, that first-person camera in the previous post was adequate, but this is more of kind of what we were thinking. So let me jump quickly to the code and show you how it works. Really, I was playing with the style interactors or the cameras from the previous post, and it's so clunky working with a keyboard and a mouse that after the ARX program I really wanted to just give a quick overview of how difficult it would be to bring in head tracking so that you could naturally just walk around in the 3D environment. And this is for like a pilot type approach, or an observer, someone that would move around and interact in the 3D world that the bots are in. The ideal scenario would be to have a Rift, an Oculus Rift, but I'm still waiting, and there's nothing in the mail at the moment, even though I've pre-ordered. So I picked up my old pair of Vuzix Rap 920s, and well, they've got head tracking. So at least to just quickly demo this, it's not really part of the actual the post track itself. This is more of just like a quick little intermission, but this should at least show how it's done. And then the code is available, so you can download it and play with it as you like. What you'll see is two desktops. This is my main desktop, and on the right is actually my Vuzix glasses. So they're wired up and they're plugged in, and they're running through, just quickly checking that they're alive, this one here, and they're running as another extended Linux desktop. So with the video feed at least working as a second desktop, the piece is to get head tracking in, and unfortunately there are no Linux drivers for the Vuzix, or nothing that actually works. There's some good kind of in progress work by a couple of guys that are referenced in the blog. So I used some of their code, and I wrote a quick user space Linux driver. And what this does is this actually publishes the head tracking units, or the head tracking orientation, as an LCM object. And this LCM object or message can then be picked up by anyone to pick up where the user is seeing. And this is then brought into Python in the normal bot environment, and you can just plug that straight into a style interactor or a camera as a first-person camera and then fly around the environment. I've also plugged in the Peregrine glove just so that I can move around by touching, you know, my fingers together. That isn't really necessary though. So, I mean, the prerequisites of getting this working is that you need a head tracking that you can publish to LCM, and if you don't mind using a keyboard, you can use a keyboard to fly around. If you've got a power glove or a Peregrine, well, it makes it a little bit easier, but they both map as keyboards, so you don't really need to worry too much about that. The biggest problem is to get head tracking into LCM so you can pick it up in Python. So what was done here, and this is a little code blocks project. The code blocks project literally just connects to a device. Let me just quickly find out where it is. It connects to dev/hydraw0, and all just as a quick bit of background, this is by Justin Heinemann and Hendrik Polocek. This is some of their code which we've adapted for this purpose. They actually wrote an original driver. I've now just modified it a little bit and got it to work so that we can the RAP 920 to work properly. So anyway, you literally just connect to dev/hydro0, and that is just binary publishing of the orientation from the VTK. So if you actually cat that, you'll just see a lot of stuff coming out. But this piece of code takes that, it parses it, which these guys originally wrote, fantastic code, and once it's parsed it, the last piece to really do is to push this out into LCM. So the main loop is really straightforward. You connect to the attitude sensor, so this is a slightly modified version of it. Download the project from the post rather than the project from their blog if you want it to work out of the box. But the attitude sensor is roughly the same. So it connects to the attitude sensor, then it creates an LCM channel. Then all it does in a while loop is it reads the orientation matrix from the kind of the user space driver, and it publishes it out to LCM as a message, and the message is called SemiSorted head tracking. Once you have that and you run this application, you go through a little bit of calibration before it actually works properly, and that's all coded in here. It's a modification that was added in. You'll actually, if you run it, you'll get this. It'll just show, here's my head tracking measurements, and you can see I've been using the glasses for a while and they've been drifting, so the yaw has wound up quite a bit, but it still works. So here I'm pitching and I'm rolling, and you're reading the measurements out. Now this is being published to LCM, so you can take that from LCM and you can push that anywhere. What I've done is I've slightly modified the bot project to add an LCM channel in. This is called head tracker, and all the head tracker does is it reads the message, so it decodes the message when it's running, and then it pushes it into a little head tracking orientation vector. So this thing runs in the background and it just gets messages and it writes to this head tracking orientation vector. Then I've built a secondary camera based upon the first person user camera that instead of using the mouse to pick up the orientation, it just goes and creates one of these LCM channels, and this is slightly hacked in. It's literally just a weekend demo, so I mean I would strongly recommend cleaning this up a bit if you wanted to actually use something like this, but this is at least a proof of concept. It goes and it connects to the LCM channel inside the camera, and when the LCM channel updates, it literally goes and sets up the camera. So every 10 milliseconds it goes and connects and says, oh, you've got new LCM data, let's go and change the orientation of the camera. When you've run this, you're going to get the user space console application that's publishing this LCM data, so that's then the producer. We don't really care where that information comes from, as long as in LCM we can go and connect to a channel, and the LCM channel is actually, in this example, is, give me one second, oh sorry, wrong file. The LCM channel is called Pilot J Sparrow. So theoretically, if we had a lot of users, we could publish, we could subscribe to Pilot Star, and then we would have all of the pilot's informations coming in, or all of the pilot information from, that's a rough one. We would have all the information from all the pilots coming into our visualization environment, and we could then draw them in space. So you can actually see where the different users are looking, and I'll actually use this in the November kind of hackathon session to demonstrate how multi-role or multi-user or even multi-pilot approaches would work. Now, this is a little proof of concept. I had a few hours free, so I thought I'd write the driver, and once I wrote the driver, then plugging it in here was relatively easy. I thought, oh well, I might as well just share the code if anyone wants to use it. So without further ado, if you have the measurements, the console application is running and it's publishing that data to LCM, then all you do is you run this code, and I'm actually going to put the glasses on, so I'll put a little movie in here to show how it works. So here you can see the video feed from the glasses, and I'm actually pitching my head up and down right now. I have the peregrine glove on, so I'm quickly going to move forward and fly towards the original setup where we've got the bots all lined up in a circle. And that just involves me pressing my index finger to my thumb. That's not a great way to move around in a scene, but it's better than being tethered to a keyboard, because I can at least move around and look around now. The Kinect is a much better approach, but it takes a bit more work. So here I'm now flying into the scene and I'm looking around. It's a lot more immersive. It's difficult to describe in a video, but if you try it with a pair of glasses, it really makes a big difference than just seeing a flat screen with a scene in it. The head tracking isn't great. I think their Kalman filter needs a bit of work, but it's adequate at least for this purpose as a proof of concept. So this pretty much concludes the branch, just to kind of demonstrate how to build a more representative style interactor. From this point on, I'll go back into the posts and complete the PyQt tutorial, and then the LCM, because this component does use a little bit of LCM, and I didn't describe it in a lot of detail. In post 5, I'll go in a lot more detail on how that all works and how the bits and pieces fit together.